By the end of the video, you'll understand friction in physics problems and also inclines. So let's start with what is friction. So imagine a surface and you have some kind of object on this surface. When this object moves in one direction at a certain velocity, friction will always be in the opposite direction of that velocity. Today we're going to focus on two types of friction: sliding friction, which we call kinetic friction, and another type called static friction. Now what's interesting about friction is it doesn't really depend on the surface area of the two objects in contact. Really doesn't matter that much. So from that information, we make a simple model of friction, which is Fr for friction equals this symbol with a K. Now this means the coefficient of kinetic friction times the normal force. So that means friction is connected, or it's in some way approximately proportionate to the normal force between the two surfaces rubbing against each other. Unlike things like Newton's first law, this is not some rigid equation. It's more just a general relation between the normal force and friction. It's what we're going to use to solve our problems today. This here, the coefficient of kinetic friction, depends on the material of the surfaces. So how wet, how dry, how rough the surfaces are. For example, if you were rubbing wood on wood, it would be 0.2. If ice was sliding over ice, it would be 0.03. And if steel was rubbing against steel, the coefficient would be 0.6. So that's it for kinetic friction. But how about static friction? So what's the difference between static and kinetic friction? Well, take a box, okay? Kinetic friction happens when you start sliding the box, and kinetic friction appears to counteract that. Static friction, however, happens when the box is still, when it's not moving. Well, how can friction be acting on something when it's not moving, right? Well, let me give an example. Let's say you're driving your car. This is your car, but it's not starting up. So you're going to push it with your hands because you're really strong. Yep. And you put a lot of force into pushing this car. You give it your all, but it doesn't move. Why doesn't it move? That's because static friction is pushing against your force. The harder you push on this car, the more static friction arises. When you finally gain the strength, let's draw our muscles, these are your muscles, and you gain the strength to finally start moving this car, you have overcome static friction. And then from there, it's kinetic friction happening instead of static. So when you're not pushing the car is just staying there and the static friction is 0. But when you push it, it has a maximum before the object starts moving. So because there's that range of static friction, the model we'll use to describe it is Fr is equal to the static coefficient of friction times the normal force. So it is the same as the other one for kinetic friction, but the coefficient is a different thing. The static coefficient of friction is always higher than the kinetic friction because it's harder to start moving something than to keep it moving. Let's go through an example. Let's say this is a road and we have a car on the road. So like this. Yep, nice pretty car. If the static coefficient for friction is equal to 0.4 and the coefficient for kinetic friction is 0.3, how many newtons of force does this car need to go forward at to start moving? Now your car is 1,000 kilos, and let's draw our forces. We got friction, and that happens when our car moves forward. So let's start with finding the maximum static friction, which is the coefficient of static friction times Fn, right? And that's equal to Ffr. This is what we were looking at earlier. This is equal to 0.4 times the normal force. What's the normal force? So the object is at rest, right? Our car's not flying away into the sky and it's not sinking into the floor. Vertically, it's at rest. The zero vertical acceleration. So the normal force is equal to gravity. The pull of gravity, as we know, is 1,000 kilos times 9.8. So that is 9,800 newtons. That means the normal force counteracting that is also 9,800 newtons. So go ahead, plug that in. 0.4 times 9,800. The maximum static friction is 39 newtons. That means if we want to drive our car forward at all, then we must be moving it forward with a force greater than 39 newtons. So like 40 newtons, that's enough. Here's another example. It's like the kind of problems we were solving in the last video, but we're going to take into account friction now. So let's have a surface and we have a bag of flour. This bag of flour, we're trying to pull it by a string. And we're pulling it with a force of 60 newtons, 42 degrees above the horizontal. If the coefficient of kinetic friction, so this thing, is equal to 0.3, what is acceleration? And also, by the way, it's 10 kilos. Let's start by labeling the forces. We have gravity and the normal force. And we also have friction. I like to draw friction on the floor like that. So let me test your understanding when it comes to solving problems like this with free body diagrams. What is the next step here? The next step here is to resolve the vectors into their components. I'm not going to walk you through the process because we've done this a bajillion times. The horizontal pull, which is this, is 44.58 roughly. We don't have to worry about the vertical pull component right now because we're looking for horizontal acceleration. So let's apply the second law. The net forces in the horizontal direction is our horizontal pull here subtracted by friction, because friction is acting against us. So it decreases our net force. But what is the friction? Let's use our formula of friction equals kinetic coefficient times Fn. The normal force when an object is at rest vertically is equal to gravity. However, we have a vertical component here, which it seems that we now have to solve for that. Let's go ahead. Fpy is equal to roughly 40.14. Now apply the second law to find the normal force, which is Fn minus mg plus the help of our pull. The normal force is 58 newtons. Now we can take this back here. So this is equal to 0.3 multiplied by 58. This gives us 17.4 newtons. That's the force of friction here. So really it's just a game of finding the variables and vector math. Let's go and plug in our values. So we have our horizontal pull being 44.58 and our friction, which is 17.4. That's our net force in the horizontal direction, which is also equal to mass times acceleration. And that's of course because, F equals ma. Let's solve for acceleration by dividing by m. And you get this right here. A equals 44.58 minus 17.4 divided by m, which is equal to 10 kilos. This comes out to 2.718 meters per second squared. That's how fast our bag of flour is going to get dragged across the floor. So if there wasn't friction, then it would be something like 4.4 meters per second squared. So friction is slowing us down, which is how it works. What about inclines? Inclines are interesting because you have to solve them differently to any other kind of problem. Let's say you have an incline and you have your box. Gravity still goes straight down. But here's something you need to do. When it comes to your coordinate system, usually you choose like X and Y going like this, right? But you don't want to do that here. It's going to make it much more complicated. So what we do instead is we set Y to be perpendicular to the surface and X is parallel to the surface. That means gravity is no longer straight down on the y-axis. It's at an angle. So when solving for incline problems, you now have to break down gravity into its y and x components. Before we start, quick reminder, gravity is always straight down. If you're on Earth, it's going straight down. Let's run this through one example. Let's say you have a kid and he's on a slide. Here's your slide. And we're going to represent the kid with an easy shape. We'll just use a bowl, I guess. The kinetic coefficient of friction is 0.10. The slide is at an incline of 50 degrees. Then how fast does he accelerate down the slide? Let's make some space so that we can draw our free body diagram. First, of course, we have to make it clear. This is y and this is x. There's gravity acting on the kid, which is mg. There's also the force of friction, so Fr. And what's pulling him down the slide would be the x component of gravity. Does that make sense? On normal flat ground, you just get pulled straight down. But on an incline, you get pulled straight down and you start sliding forward as well. So first, we're going to need to find this component, this x component of gravity. We can get this with the formula mg sine 50. And you might be saying, what sine? It's in the x coordinate though. And x horizontal is always cosine. This is what is a little tricky to understand. When you're on an incline and your coordinate system is rotated like that, and you're looking for gravity, the trig function, the trig ratio that you use is different. And let me try to explain this to you. You have your y coordinate and your x coordinate. Your gravity goes down like this. If you're looking for this, the x component of gravity, then it forms a triangle, yeah? This angle here is 50 degrees, and we know this because of how interior angles work. If you went and jumped around with all the angles, then you would find this is 50 degrees. So sine of 50 degrees, this angle inside here, is opposite, which is here, over hypotenuse, which is gravity. And same with the y component. The y component is this. And because of interior angles, we know this is 50 degrees. The adjacent side over the hypotenuse. That means the y component is cosine 50. You don't have to understand this completely. It's a pretty annoying thing, honestly. But just remember, when you're solving problems on incline, gravity has flipped trig ratios. Horizontal uses sine, and vertical uses cosine. If you're in a rush, just understand that. Moving on from that, let's find his normal force, because we're going to need that to find the friction, right? So the normal force is acting here, perpendicular to the surface, because that's always how it is. The normal force will be counteracting the y component of gravity. This is equal to the normal force. Let's apply Newton's second law to find the acceleration of him going down parallel to the surface, which is, just going down the slide. The vector sum of all horizontal forces, the net horizontal force, is, of course, we have mg sine 50, our horizontal pull, which is this force here, minus friction, because friction is acting against us. And as you know, friction is the coefficient of friction multiplied by the normal force. And the normal force is mg cosine 50. So let's write that, mg cosine 50. This is also equal to ma because of Newton's second law. Here's where something interesting happens. We can cancel out mass, because if we divide both sides by mass, mass is gone. Now we can solve for acceleration. Gravity times sine 50 minus the coefficient of kinetic friction, cosine 50. plug in your values. So, and this, the grand answer after all this solving is 6.88 meters per second squared. There you go. He accelerates down the slide, so parallel to the slide. He accelerates at that speed. For every topic I cover, I like to create a free cheat sheet, and I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.